Kia ora koutou, everyone who's listening. Thank you all so much for being interested in this. So my name's Henry Seaton. I'm an undergraduate student here at UC, and this is a recording of my summer project presentation, which is about conduction losses in cryogenically cooled gallium nitride devices. This is part of a much larger research program, and this is a record of my work as an undergraduate summer student over the 2020-2021 summer holidays. Briefly, what's in this presentation? I'll go over the background and the scope of this research, why I selected this project scope. I will talk a bit about the experiment that was conducted and how we set this up, and then about the results obtained and what those mean. I will end with my conclusions, areas of possible future development, and lastly, some supporting notes on appendix data that wasn't included in the main presentation. Starting with the background. So, this is part of a much larger program of work, which is aiming to create large-scale sustainable electric transport. The big challenge in this is creating a motor which is powerful enough to support a car, a train, or an airplane, but also light enough to be able to fit to a vehicle and easily be handled. The currently proposed solution is a superconducting AC motor, but this needs to be cooled to extremely low temperatures in order to work. This research focuses on the power electronics that will be used for such a cold motor, and seeing if by cooling the electronics as well as the motor itself, we can get any sort of improved performance, or even if this is possible in the first place. For these power electronics, we looked at using gallium nitride transistors instead of silicon-based devices. So gallium nitride is an emerging new type of semiconductor, and this has a lot of advantages over silicon. In particular, it can support higher switching frequencies with lower on resistance and can support greater maximum voltages for the same size device. So this was a strong area of interest for this research program. There are two main types of gallium nitride devices we looked at. So first of all, we have EHEMTs, or enhancement HEMT devices. So this is just a single true design which consists of one transistor switched at the gate terminal. The advantage of this is having a single device is simpler, but the downside is that because this is quite a new technology, the manufacturing of this, or the matching with a silicon control circuit, isn't always as good. Conversely, you can get cascode devices. So these have two transistors in them. You have a gallium nitride HEMT, and then you have a silicon MOSFET, which acts as the drive and is attached to the gate terminal. So this is a lot easier to manufacture and to control, but because it's more complex and you have different devices in the same package, it can create noise issues or be less effective overall. The scope of this research. So transistor losses consist of two types: the switching losses from turning on and off dynamically, and the conduction losses from on resistance. So this experiment focused just on the conduction losses, partly because of time limitations, but also to get a very accurate measurement of on resistance with our tools that we had. So the goals of this research were therefore measuring this on resistance and using that to work out how conduction losses changed at different temperatures, but also comparing how different types of HEMT devices worked and if one was notably better or worse than the other. So moving on to the experiment design, how do we test this? So the first step was choosing the transistors that we were going to use. And after some market research, we ended up picking these two devices that you can see here. There are other manufacturers on the market, but not many. A key reason for picking these is their maximum voltage limit of 650 volts at room temperature. In future years, there may be better performing devices or devices with higher maximum voltage on the market, but as of right now, these were very effective based off our research. How we tested these. So we used a very, very simple PCB and a circuit to evaluate on resistance. This was just a physical mount for the device itself in whatever package it was needed. We had a gate source voltage of 6 volts as per the data sheets, along with some gate side protection against overloads or surge currents. To measure on resistance, we used a constant current from drain to source, This was set at 1 amp as a balance between getting an accurate measurement and not having too much power dissipation. And then we used a voltmeter to measure the voltage drop and therefore the resistance of the device. To measure temperature, we used a PT100 temperature sensor, which was attached physically to the surface of the package, and then used a data logger and a similar method there to measure the temperature of the device package. In our test rig, the key consideration was making sure we could mechanically insulate the test circuit from liquid nitrogen or from heating to prevent any damage. So we end up using this handy little polycarbonate box you can see in the top right here, and use two cables, one which carried the drain source current and another which carried the gate voltage and all of the smaller signals. For the test, we ran these two in series along with a shunt resistor we used to measure the current. We then used two data loggers. We used one to measure the shunt resistor voltage drop and therefore the current, as well as measuring the voltage drop across each device. And then a second data logger was used to measure the performance of the temperature sensors and what temperature the device was at. Temperature control. We wanted to get as big a range as possible of temperatures in order to have an accurate model. So starting from the coolest, we used liquid nitrogen to cool the devices all the way down to -196 degrees Celsius. This was a gradual cooling process over a few hours each way. We used gas in a covered box to drop the temperature to about -150, but then eventually submerged the boxes entirely to get a full range of data. We also used a chili bin near room temperature. This was just to get more accurate data in this range of 25 to 0 degrees Celsius. And lastly, we used a temperature controlled oven for temperatures up to 100 degrees. The oven is a bit outside the scope of cryogenic research, but because we could control this oven quite accurately to set the temperature, it was useful to get a further range of data to validate our model. So moving on to results then, what did we find? So this graph here shows our overall results over all the temperatures, and you can see right away that the data from different tests with different apparatus do match up over the entire 300-degree range. So there's a few different features here I'll talk through, but I will start with talking about the performance of each device in and of itself. So you can see here the resistance when it's on of both the eHEMT and the Cascode devices. And you can see that the eHEMT had a low resistance at room temperature, as expected from the data sheet, but also dropped a lot more when you cooled it. So these normalized values on each device are relative to the room temperature value. So you can see that when it was cooled to -196, the eHEMT device dropped to as low as 18% of its normal on resistance. So that corresponds to an 82% saving in conduction losses, which is really awesome. Conversely, the Cascode device also decreased in on resistance, but not quite as much. At most, it was a little over half of its original on resistance, and as you continued to cool, it actually increased. So that was another interesting feature, was that the eHEMT device, which was only one gallium nitride transistor, continued to decrease in on resistance the lower you cooled it. And based on this model, you'd expect it to continue to decrease if you cooled below -196. However, the Cascode HEMT actually had a minima at about -135 degrees, and then if you kept cooling, it would increase in on resistance overall. Now, this is likely due to the silicon MOSFET on the gate side. Silicon does increase in resistivity if you cool it too much, as per previous research, but further comprehensive research and testing would be needed to validate this. Another factor too was that, as we've said, the eHEMT device varied much more with temperature than the Cascode MOSFET. So because of this, there must be a point where they intersect. When we did our heat testing, we found that there was an intersection point of 59 degrees C, and at temperatures above that, the eHEMT device was actually less effective because it increased further in on resistance. And this meant that the cascode hemp, which was less effective at cryogenic temperatures, may be better for high temperature applications. Lastly, repeat testing. So we didn't do much in this area, but we did validate the initial tests by using a second eHemp device in the oven at the same time as the first system. So from that, you can see here that there is some difference, both in their room temperature values, but also as they're heated. But the normalized difference is about 5% overall. So this means there is some variation in the trend, but also the trend is fairly consistent, all things being considered. Future areas of research could be some large-scale testing here with many more eHemp devices or other types of devices to get a more consistent model. So lastly, what does this all mean? So in conclusion, we found cryogenic cooling did drop the on resistance and the conduction losses of gallium nitride devices. In some cases, this was a massive power saving of over 80%. Of these devices, the eHemp we tested from GaN systems performed much better, and subject to testing other parameters like switching losses, this would be a good device to consider for future development. Possible areas of future research. So as we've said, this is aimed for design of a motor driver, but could also be used anywhere that needs high power, low temperature systems. Another option could be developing the model of gallium nitride devices at these temperatures, doing some large scale testing of multiple devices or different models. And one possible application of this could be integrated temperature sensing. As we have seen, the model is consistent within a certain margin. It may be possible to measure temperature from the device itself and therefore not need a PT100 in industrial uses. Acknowledgements. This work was funded by MB through the Robinson Institute. Thank you very much to both of them for putting this all together. And also a big thank you to the research supervisors, Dr. Bill Heffernan and Dr. Andrew Lapthorne, for all their support in making this project happen. Thanks very much. There are a few appendices on this slideshow. These are not part of the main presentation, but I will talk through these now for people who are watching. The first set of notes briefly explaining how we picked the parameters for testing. So as I touched on before, we used a 1 amp drain source current. This was because we needed current to be above a certain level to get an accurate measurement of the voltage drop and therefore the on resistance, but also using any higher current in the tens of amps range would mean there was massive power dissipation, which we did not account for. So high voltage testing would need to consider this. The gate voltage of 6 volts, that was recommended per the data sheets. The devices did have different maximum gate voltages, but both said that 6 volts was fine. And the gate resistance and gate source resistance were all picked just as a rough order of magnitude size. That is because as temperature varies, resistance varies, so there was no point in sizing these precisely. And then lastly, the Zener breakdown diode, we picked that for the 7 volt limit for the eHemp device, but which is consistent across both devices. Secondly, forecasting. So based on these trends, we would expect the eHemp resistance to keep dropping. So I've used an exponential model here. Whereas as the cascode device increased in resistance, we used a polynomial quadratic model. So based off this, theoretically, you could get the eHemp resistance down to about 1 or 2 milliohms, or about 10% of its room temperature value. Whereas if you cooled it all the way, the cascode device could increase almost the same value as it was at room temperature. These models obviously could use more data, particularly at a larger range of tests or by testing at lower temperatures, but this is just some indication of what the starter from the starter alone. Lastly, a key thing to consider at low temperatures is that the resistance and the voltage drop measured across the device actually includes more than just the device itself. So because the device is in a package, you have the die, but also the bond wires and the solder layers as part of the package, and the resistance of the copper trace of the PCB. So this is effectively a series of resistances, and we're measuring the voltage drop across all of them. What this means at most temperatures is not much, but as we cool the device down and the resistance of this drops extremely, the resistance of other parts may come to dominate this. So a possible way to get around this would be getting access to the die itself and placing the probes even closer to the transistor, but this would take further research and a more sophisticated testing rig to test. Those are all the appendices I've got to discuss. Thank you very much for listening, and please feel free to email me if you have any questions or like further clarification.